Okay. All right, it's recording now.
Okay, thank you then. So, welcome everybody. This will be our second workshop on Spark. So, framework for big data, and in particular, this one will be the first one on machine learning using Spark. And this will be very interactive. So the idea is that I hope all of you have your own accounts on Thorny. I noticed that some of you request for an account recently, so that is very good. So what we will be doing is I will introduce you, for those of you who didn't attend last month, our previous workshop, how you access Open on Demand. All of you, if you have your accounts on Thorny, you can do this. And after, we will start working on the notebooks, and the Jupyter notebooks with the Spark, and we will go through the material that I prepared for you today. My name is Guillermo. I work here for Research Computing, the research office. So let's start with this. The time for today is pre-pack, and this will continue on a new workshop around 1 month. So again, with machine learning, so we will be going through several lines of workshops related to this area, machine learning, and taking advantage of Spark for this. So the first thing for you to do is to go to this website on demand. So I will actually copy this and paste it on the chat. So please go there. The first thing that happens is we'll ask for your credentials. On W, you go your cell phone Duo, you enter, and if everything goes well, you should land on a web page and a dashboard like this, what you are looking right now on your screen. So the idea is that somehow you manage to split your screens so you can see what I am showing you, and at the same time you are able to reproduce, to follow the materials on your own. So I will give you a couple of minutes. In the meantime, I will be transferring the most recent version of these materials to the location where you can copy that. So please, the idea is you to be at least at this point. So we have here, I see 12 people, 13. So if the number remains like this, feel free to just pose the questions and mention. We have Daniel, we have several people here who can help you in case that you get stuck in something. This will be very, very soft introduction to machine learning. If you are familiar with machine learning tools, you could eventually be disappointed, because this is a very soft introduction for many people who is not familiar with the material, is not familiar with the Spark. I hope people is sufficiently literate on Python. That's the very minimum. But even though the kind of things that we will be doing are relatively simple. So, so you will be able to follow the material, even if you are not a Python developer or anything like that. So I hope all of you are on this webpage. You are able to see this on your browser. And now we will copy the material to your home folder. For doing that, you click here on clusters, and after you click here on Thorny Flat Shell Access. So you will see a new screen will pop up. And let me see, will go here just to show you. Okay, you can execute the command here. I will not do it that because I already have it. For mini workshops, Spark Pipe, and you execute this with the tab. So this is the command. Let me see if I can copy this. Not sure. I can copy this in the chat. Yes, the URL is on the chat, but I will copy again, because if you enter after I posted, yeah, Jason, do you have it now? Okay, perfect. And I will try to see if I can copy the command, just in case. So this is a Linux command. Everything in Linux is case sensitive. So you need to type this exactly as I put it there. Share software Spark Python. That is the command, and hopefully I type it correctly. By the way, the idea here on this terminal is for very quick commands, so the terminal kills itself after a couple of minutes. Let me see if I can go here. Yeah, it didn't. So I will retype the command. So share software. By the way, when I am typing this, for those of you who are not familiar with Linux commands, you can always hit tab to complete the command. So share, I know that it's in software, so just type the first 2-3 letters and hit tab. It will complete that mini, and it complete the entire word. And it's Spark Python, and put it here. By the way, remember to remove the last slash, because with this command, there is a difference between putting the slash or not adding the slash. So remove that and copy that to the folder. Hopefully this, yeah, I have exactly the same. So the advantage of this command for copying files is that if you do it multiple times, is idempotent. So it will not do anything. It just checks that the files are there and exactly the same, so will not copy anything again. That's the first step here. Let's see. Oh, okay. Yeah, for Eloisa. It seems that you have exceed the quota on your home folder. It's something that we can check later how to do that. But I will show you a way to bypass this right now. Let me see. And in the meantime, probably Nate can try to free a little bit of space for her. But if not, I will show you an alternative. And I think that I see. or Daniel or Nate, can you check if you can free a little bit of space? I don't know if putting the files on the Scratch will work. Okay, thank you, Nate. So that is another option. Instead of putting a dot, you put a Scratch. That way you will be copying the files into your Scratch folder. So you have two places to put data on the cluster. The home folder, which is limited to 10 gigabytes, not much, but that is that is space, receives backups, so it's more resilient, but it's small. Scratch, we have hundreds of terabytes there. A few terabytes is still free. So there, I think you can put up to 30 terabytes of data without much trouble. And most people use 1-2 terabytes of data for research. So that is an location that you should prefer if you are dealing with large amount of data. I never mentioned this because what I have for the material for today is relatively small examples, small data. But that's an alternative. Hopefully all of you were able to copy the data to your home folder or your Scratch, and you are able to, yeah. Now let's see if I'm able to do this. Let's do it again, because I'm not super sure if I copy this to the Scratch, if I am able to open it from the Scratch. Let me see. I didn't test that before, so I'm leaving here. So now let's start with this. Now go back to the page, the dashboard for Open on Demand, and now click here on Interactive Apps. And click here on Jupyter Official Images. Yeah, you should get something like this. Official Images, please go here. So Jupyter Official Images, select this one, Jupyter Notebook Python Spark. It's called PySpark Notebook in parentheses. So click there. So that's the image that we will use for these tutorials today. Here the queue, so where we will be requesting for resources, which queue. So the system, the cluster offers several queues. This one is something that will give you pretty quickly, eventually, a job running. It's limited to 4 hours. So here you can put up to 4 hours. I am adding 4 hours, even if we will just be working for a couple of hours. CPU cores. So as you will see, one of the advantages of Spark is that it's scalable. So you can use, contrary to other packages for machine learning that are more popular, but are limited to use just one core. But this one can use multiple cores and even multiple machines. So if you are really dealing with big data, which means many terabytes of data, and you need to process all that, so one machine is not enough, you can even scale up to as many machines you are able to get on a cluster. For this, all that we are doing is very, very simple. So a couple of cores just to allow all of you to get, we have like how many? 11. So all of you get an idea of what we are doing today. So please request 2, maximum 4. You can request up to 40, but if you request too many, you are pushing other people to wait, or you will just keep waiting for getting those sources. So 2, 4, This is okay. No GPUs. We will not be using GPUs here. We will be just dealing with classic machine learning, so not deep learning. And now hit launch. And now, what happens now is you will see in a screen like this. It says Jupyter official images, 4 hours, 1 node, 2 cores, and in a minute you will see a button popping here. Yes, and now you will see this button here in blue, and it says connect to Jupyter, and you keep there. So now let's see if I am able to go to my Scratch. Oh yeah. So if you copy your data to your home folder, you will see a folder like this, Spark _ Python. If you don't, well, that's the point. You can't go there. Yeah, I can go into my Scratch because I have a sim link there for my Scratch. Okay. Well, something that we can do is, again, go back here, and there is probably a way, but what I do typically when I work on a cluster is that I execute these commands: ln this s scratch this scratch. So I create a symbolic link, which is let me see. Okay, yeah, that's okay. So for I think it was Eloisa, you can re-execute the command before, copy the material to your home folder if you prefer, but because otherwise the way to get into the to see the Scratch folder on the Jupyter notebook you need to create a symbolic link. Probably there is another way to jump into the Scratch, but by default it will just show you the content of your home folder and will not allow you to go up, I think. So now all the materials is here, and click on the Spark Python, and after click here in notebooks, and we will be using notebook number 4, Spark and machine learning. We will see how far we can go with this. So I hope all of you are able to open this notebook. By the way, now you can execute the cells on the notebook. If you execute them and you get an error, it's probably because you forgot to execute another box up in the pile, on the notebook. So this is supposed to be executed in sequence. So let's do that, and let's start working. So how you execute a box on a Jupyter notebook? You go to the box, and it's in editing mode. You know that it's in editing mode because here you see a green bar, contrary to be in command mode, which is just a blue bar. So here you click inside and you will be in editing mode. To execute this box, you just hit press shift and hit enter. And you will see that the screen change. This is a brand new Jupyter Spark image. So you will be using the latest version of Spark, the latest, very recent version of Python, IPython. All the tools are very recent. So this should work in principle with the latest version of the software for all the Python packages that we'll be using today. So what else? Let me see, execute this. I will be using, I'm executing this for steps here. So you can check here the versions that I'm using. In case that you can take these notebooks, by the way, you can transfer those notebooks to your personal computer. If you have a Spark there, you can install a Spark. It's not that difficult, actually. And you can execute this from your personal computer, no problem. And all the examples are relatively small. So at this point, you can work with this. So this one comes from our previous workshop. This is the typical commands that you get, that you have to use when you are first working with Spark. Create a Spark conf and create a Spark context, at least loading the module and create this couple of objects that will be needed for most of the executions. Basically, all executions use the Spark context, except for a tiny little part that uses data frames, and that's a slightly different story. So first, my purpose here is introduce you to the area of machine learning. I hope, or I expect you are not familiar with that much with the area, so that justifies a small introduction on this. So you can think machine learning from the scientific point of view. What scientists do first, it gathers some data, an observation of the world or an experiment, and try to gather, to generalize those observations or into a theory that usually is spread in the language of mathematics that is capable of answer questions related to the phenomena that you are looking, and eventually produce predictions, and those predictions can be corroborated with further experiments or observations. The important point here is that the first part of the whole process is gathered data, is making observations. For example, astronomers cannot make experiments, they do observations. People in other areas do experiments. So it will be between experiments or observations somehow, and gather data. And after is a human, your intelligence and your skills in mathematics, in science, on different areas that allow you to synthesize those observations in something that allow you to model that give you predictable power. Now, the role of machine learning is to create those models that are able to predict or they are able to explain some behavior or some phenomena with just from the data. So that is the learning part of machine learning. Just taking the data and using a procedure, an algorithm that you know, but you don't know how the algorithm will work. Well, you know how the algorithm will work, but the algorithm is not prepared in advance to produce a result. It will take the data and it will follow the procedure to produce the model that is able to predict the outcome. So the central word here is data. It's basically an algorithm that captures patterns. There are several tasks or several areas where you use machine learning, and traditionally has been described like this: the area of classification, which involves also regression. So if you are trying to separate something into good or bad, cat and dog, a pulsar, not a pulsar. Those are classification problems. And if you are trying to gather an equation or a model that is capable of predicting the outcome or something that goes in a continuous, that will be a regression. But that's one area. Another area could be clustering. So you have usually in very large dimensions phenomena that can be observed thanks to a set of variables, and you gather all that data and you ask, okay, if I observe this set of variables, which category or to which cluster that should belong? At that moment, we don't know in advance the points that were given and where they belong. So that is another kind of problem. As you will see, a lot of the big area of machine learning deals with very high dimensions. So hundreds of dimensions, a number of dimensions that you can no longer observe. So the algorithms are created, and the techniques and the objects, and this is very important, the objects that we will be dealing with for machine learning are usually created to manage very large dimensions of data. The good thing is that for the examples and all the materials, we will be going into 3, 4 dimensions, hopefully 2 dimensions, and we can try to do something with that. Anomaly detection, so trying to find something that escapes the regular observations, or something that is, again, anomalous, or something that goes an outlier of a certain. So how to detect that? So let's review a little bit what is called like a taxonomy of machine learning algorithms. You can divide, you can categorize machine learning algorithms as one classification of supervised, unsupervised, and reinforcement learning. In the supervised, which is, for example, classification and regression are typical examples of that. You have some data, an input data, and you know the result. So you have a set of images of cats, and you know that those are cats. Or you have images of dogs, and you know you label them as dogs. And now you will present a new image, and you will try to classify that image, allow the algorithm to decide if that is a dog or if it's a cat. So you know the correct result, and you use these 2 sets, the input data, images, or just a vector of observations or properties, whatever, and the correct result that you want, and you try to predict new results for new data. That's supervised learning. And supervised learning, you just have input data, but you don't know how that separates. But you, in that high dimensional space, there is a natural clustering, for example, of that data, and you try to discover the patterns, the structure that underlies that distribution of data. The typical example of that is clustering. And reinforcement learning. In reinforcement learning, you have the input data. You have an output, but that's a not definite output. You have something like, it's going in the right direction, it's going in the bad direction. This is going good, this is not going so good. And with that fuzzy information, like a grade function, something that directs the algorithm, you can get a better path or a better set or a better solution that goes into that direction. A typical example is training a computer to play a game, train a robot to walk, or a car to drive itself. So that is some examples of the kind of problems that you use with reinforcement. But in general, we will be working with supervised learning today, hopefully unsupervised, probably, I don't think so. That will be go for the next, and more advanced methods in those areas will go for the next workshop. So supervised, unsupervised reform. Now, I mentioned to you that a big part of this is the fact that we are dealing with very large dimensions. We are used to just 3 dimensions. We live in a world that apparently physics says is around 10 dimensions for extreme theory, but that's another point. But this is another thing. So we are dealing with data for which we have long vectors, eventually very long. And that is the space where those variables exist. And you cannot simply reduce that to having a couple of them. But some techniques exist for reduce the dimensionality of that problem to something that is more manageable. Another reason for this is that if you compute, for example, with a traditional points in the space, and now imagine points in a line, points in a line. With points on a straight line, you can take a ruler and you make the distance, and that's it. Now, if you put points in a sheet of paper, you can put the points there, and you can take a line and make the distance. Now, points in a space, you can compute those with the Euclidean formula. And you can extend that for points into an n-dimensional space. What happens is that if you throw points in n dimensions, is the most likely situation is that those points are extremely far away. As you increase the dimension, so increase the distance between points. It's just the fact that you apply the Pythagorean extension for distance, and the points will separate beyond control. So that is part of the reason why we call the curse of dimensionality. The distance between points grow much faster than you can manage. But there are techniques that you can use to reduce the dimensionality of some problems. And very nice way of seeing this in action is by using what is called a principal component analysis. We will be dealing with this in the next workshop, but just to gather, this is just a motivation section, just to motivate the subject. So it will be very visual, not mathematical. So try to see how you can gather those blue points that you see here on the screen and projecting in a line. So you have those blue points, and you see that those blue points are not randomly covering the area. They are up to some point aligned. So there is a preferable direction. The PCA, the principal component analysis, is one of those techniques that you can use to detect which is that preferable direction. You can do that by drawing a random line and making the projections, and after declaring how you can turn the slope of the line to get a better projection. A better projection is a projection that minimizes a function. That is something that is critical. So now we are mentioning two important ingredients in many algorithms in machine learning. You need something, a way for optimizing functions, so an optimizer, and a way of deciding how bad the solution is, a loss function. So that is what this is showing. This one is just rotating, and you notice that there is one direction where you are minimizing something related to the distance. The red lines that you see here at this point is they are maximal. If you take, for example, the sum of the distance of all those red lines, you get a minimum when they are in the line that crosses on the purple line, the section. So that is one of the algorithms that we use, but this allows me to introduce several elements on the description. The existence of a optimization function or an optimization procedure, the existence of a loss function, something that how to measure how good is your output, and the problem itself, the dimensions, how you reduce dimension. Another problem, typical of unsupervised machine learning, is clustering. In this case, we have this nice figure to illustrate how that works. You have a bunch of points, and you, as a human, can see that those points are not entirely randomly distributed on the screen. You see clusters of them. How you can explain to the computer that these points here are clusters, can be organized in clusters. And now, this is something that something you can do, and you can extend this into multiple dimensions where for a human, it will be very hard to figure it out which are all those clusters, because you can no longer visualize that in more than 3 dimensions. This method, by the way, is called k-means. The idea is very nice, it's very intuitive. You start with some green points here, randomly. You select how many clusters you think you will get. So you start with a guess. You throw those points on the screen, and now you start making lines. You start to gathering all the points that are closer to that green dot than any other point. After you gather all the points that fulfill that condition, it's the closest point, that you compute the center of gravity of all those points. And you move the green dot into the new center of gravity. And you reiterate. You go back and execute exactly the same procedure. You capture all the points that are the closer to the green dot. That will give you the set of points for which you will compute a new center of gravity, center of mass, or in this case, the geometric center of those points. That's it. And you reiterate until the points no longer moves. And with that, you know which are the points that belong to which cluster and how many clusters you get. Of course, if you have 100 points and you throw 100 green dots, it could happen that all the green dots will sit on top of one of those black dots, and you have a condition where the distance between points is 0, but you are not learning anything. So the idea is to find an optimal, and that is an ambiguous term, number of clusters that you can get, and then start making the machine to work. That's allowed me to introduce a new element, is that a lot of what we are doing in machine learning start with assumptions from the very beginning of the procedure, very beginning of the algorithm, like introducing how many clusters do you expect? 4, 10, 100? Those are examples of metaparameters that are kind of things that you want like to optimize later on. But unfortunately, are those elements that you introduce from the very beginning of the problem. So that's another of the nuances of complexity that comes from this area, from machine learning. So now, this is another figure to illustrate another problem in machine learning, and it's the problem of classification. You have here on the left side a set of points, and those points you will see that these blue dots are clustered. You can see that they are somehow close together to some point, and the red points are also close together. But there are also points that mix or enter in the area of the order, so that some invaders do. And there are different versions of that. So we have blue points here in the second row here, blue points in the middle, surrounded by some red points. And here we have another situation where we have blue points on one side, red points on the right. And now you will see how different algorithms used for classification behave according to for those problems. In particular, we will see, hopefully today, otherwise for the next workshop, linear methods. For example, this linear SVM, the third row and the second row of algorithms is called linear SVM. SVM are Sparse Vector machines. It's a linear method to classify values, classify elements. So you see that this method throws lines and separate those, make a line and say all those that are on this side of the border belong to the blue, all those that are in the other side of the line belong to the red. But those are lines. So all that column only is capable of drawing lines because it's a linear method. There are other methods, like, for example, nearest neighbors. You're just saying, okay, you have an area and all the points that are closer to the red dots rather than the blue dots belong to the red tail. It's a nonlinear method. It's capable of producing a result, but it's strongly attached to the input values that you provide. So there are other methods like generalized SVMs, Gaussian processes that have different capabilities for separating the areas. So you will see that as you move on to the right, there are some other methods, for example, that are better to detect those rings, for example, those in the second row. There is a ring structure. You have a central dots, blue, and surrounded by red dots. For example, a neural net is very capable for this kind of problems because a neural net is capable for going in higher dimensions, moving the system out of the traditional 2 dimensions, and in multiple dimensions, you can separate that with a plane, for example. So you see that a neural network is very effective in that case. Now let's talk a little bit more about classification or regression. So here I have one small example to show how difficult it could be, for example, for a human to identify clusters when they go into even 4 dimensions. So here I'm creating, by the way, here at this point, I'm using another package, still not entering in Spark, and just making a visual introduction to machine learning before entering the Spark. So we are creating some synthetic data. So just some clustering dots here. And here I'm creating dots in 4 dimensions. I know that I create 4 clusters, but they live in 4 dimensions. So you get first, if you see the data, there will be, let's say I can put something like just to find the 5 points here. I can change a little bit. You see those points. Just a human looking at those points very hardly can see patterns. And after I have 100 points, you have 200 points. So even if I ask for all of them, a human can, I don't think that you can. From looking into all those points, say, oh, yeah, there are four clusters there. No, it's not so clear. And also, it's not so clear if you plot them. Of course, you cannot plot in 4 dimensions, but you can, for example, try to plot them and selecting just 2 directions. So if you have in 3 dimensions, you can make a plot of the projections in X, Y, Y, Z, Z, X. So in 4 dimensions, you can do the same. You can project in those 2 of those dimensions and get the projections of the points there. So here you see that under some directions, you can see clearly, for example, this one RK direction, you will see those aggregating nicely in 3 clearly distinguishable blue, green, red, and black sections. It's not so clear in other directions. In some directions, those points are overlapping. For example, if you select the blue K direction, so you see the reds and on top of the blacks and top of the greens, and the blue, yes, the blue are a little bit separated, but so it's not easy. Now imagine that for real problems where you are dealing with 100 dimensions. First, it will be a super plot like this, 100 times 100, making just 2 dimensions at a time. Very hardly you can see that. So at some point, you need to resign yourself and not be able to see the data as you did when you were learning this from this kind of tutorials, and trusting on the math, trusting on the algorithm, and trusting especially on the statistics that you get from that math. So that's why statistics matter, and that is one of the first things that we will do today is learning what you can get from the statistics point of view using the Sparse. This is, up to this point, is a very visual introduction to the subject. I suggest I gather a few places where you can see videos, again, still very visual, about machine learning, not particular for Spark, but in general, the areas of machine learning. Here, 3 books that I use, that I pick ideas for the materials. There are 3 very classic books for machine learning. And now let's mention a few tools that are still not Spark. But let me see. If you are not using not Spark, eventually you are used to something else, and let's see what it could be. Of course, everything in Python, we are talking about Python. And this, by the way, is not the only way of doing machine learning. R, for example, is another language widely used for the statistics. So it's natural the machine learning algorithms are implemented on R. And that's another thing that you can use that. Another languages, Java, for example, C, C++, you can get tools in those languages that could give you eventually better performance in some circumstances. Scala is another language on top of Java for these kind of things. But concentrate in Python. And Julia is another popular language. Well, it's a new language, but it's another language where this kind of algorithms could be naturally implemented. Other things in Python, somehow related to machine learning, data analysis, everything is on top of NumPy. NumPy is the numerical package or module for Python. So all those things work on top of NumPy. NumPy works with vectors, arrays. So it provides the basic layer for linear algebra for all that you need to do. On top of that, there are packages like stats models that specialize in statistics, but as part of that, you have the linear methods there. So if you need linear regression, stats models could serve you well. You don't need to go beyond that. Scikit-learn is a very popular package for machine learning, especially for the classic part of machine learning, not for the deep learning. Is well documented, is well known. You find a lot of materials on internet about scikit-learn. The problem with this is that it's constrained basically for just one machine, and in most cases, just one core, so one CPU core. It will not scale as Spark will. Pandas is closely related to Spark up to some point because they share something in common that is called data frame. The data frames in Spark are slightly different. Pandas is the main object for dealing with that. Spark is a software for data analysis. So no machine learning, just the data analysis. So everything that you can do with tables of data, rows, manipulating rows and columns of data. So Pandas. Something that is really close and probably the competition, let's say, to Spark, the tool that we saw on our previous workshop and the tool that we will be using today is Dask. Dask offers very similar functionalities to Spark. It also has something called Dask ML for machine learning. It's also scalable, so you can grow into using multiple cores, all the cores in a machine, for example, in our cluster with 40 cores, and also using multiple cores and eventually doing executions on the cloud. So Dask is another tool for that, and his tool are getting some maturity over time. It's newer compared to Spark, but it's going there. And Xgboost is another tool, also scalable for a very particular subset of algorithms that are based on something called tree boosting. So in some cases, these kind of algorithms could compete to, for example, some neural networks, do classification. They can be very flexible on the kind of problems that it can attack, but it's a kind of very particular kind of algorithm that can be used in a variety of tasks, Xgboost, and also support a variety of programming languages. So those are the alternatives, and I put you there some links for the software, for the web pages of those projects, and you can find others. This is, by the way, not an exhaustive list. And now we will enter on Spark. Why we are using Spark is because in front of you, or from the machine that we are using right now, the machine that that is running my web page here is an entire computing cluster. It's an HPC cluster. So we have more than 100 compute nodes there. Each compute node has 40 cores, most of them, 40 cores. Some machines have 52, some machines have 24, but most of them have 40 cores. So, and our definition of a small memory machine is 90 gigabytes of RAM. That's the lowest memory that we have on one compute node, 90 gigabytes. So you see that this is completely different to your normal computer, to your desktop or laptop computer. Even if it's a really decent workstation, it will be hard to have 40 cores on a machine like that and 90 gigabytes of RAM. So Spark is a tool that allows you to start small if you want to, run Spark on a single machine on a very normal computer, or move that job when you want to explore the big data on a cluster, on an HPC cluster. Spark offers one module, one section, one layer of Spark for machine learning. It's called MLlib. MLlib offers algorithms that can scale, so they can take advantage of multiple machines, eventually multiple cores, for classification, regression, clustering, collaborative filtering, and we will see several of those. You can have the models store and retrieve. You can load algorithms, store the state of an algorithm, and regain the data back. There are two versions of that, of the machine learning engine. One based on what we will be revisiting today, their RDDs, the resilient distributed data sets. And there is a new API based on data frames. So, and we will first, for those of you who didn't attend the previous, I will go in really quickly reviewing the material for RDDs, reviewing the material for data frames, and we will discuss now the first elements of how we work with MLlib on Spark. So let's start by saying the oldest and the most established object in Spark is called a resilient distributed dataset, RDD. RDD is just a collection of things, just like that. Not much structure in them. The requirements are very low for an RDD. It's just a set of things, period. We can create RDDs using, first, notice that, the first thing that I will be doing here is create an RDD from the Sparse context. And if you see here, the Spark context, it was something that we execute here. So the first step, now we are entering in a Spark, is executing this and executing this. Oh, it's great. Oh, well, yes, I will take in some. Yeah, because I already have a Spark context. I was trying to create another Spark context on the same machine. Will not allow me to do. So here, I am creating a configuration. In this case, I'm going back into the first line before I enter in the discussion of machine learning. The configuration for Spark. I put a name. This is just a random name that you can put. And here is the declaration of the resources that I am requesting for this. As I request 2 cores, you can say, okay, I will be running locally with 2 cores. It means that when you execute vectors, you can put to work 2 cores on my vectors, on my RDDs. You can partition those if you want to. And I have 2 compute engines, 2 CPU cores that are able to process the data. If you move into a larger set of data, you could be interested into changing this for 40, requesting the 40 cores on a machine, and now you have 40 cores attacking your data, partitioning the data, and all working together for your process. And the first thing that we are doing here is creating a Spark context. So now after that, I will move in here down. And we will be reviewing how we create an RDD, because we will be using this. So for those of you who didn't attend, I just introduced that. You can review the other notebooks later on to check that more details about RDDs, transformations, and actions. So here, I'm creating an RDD with just a list of data. The first line is a Python list. A Python list. The Python lists in Python are extremely inefficient, are very flexible, very inefficient. The next thing better than that is NumPy array. It has more structures. All the values must be of the same type, but allow you better performance in many cases. But still, with that, you can create an RDD just using the method parallelize for that list, and you are creating an RDD. Now, with an RDD, you can do two things, basically, a transformation and an action. Transformations are lazily evaluated. It means that when you execute something that is a transformation, nothing happens. It just records that you want to do that, how the transformation works, but the data has not been touched. Nothing happens with the data until you trigger an action. An action for an RDD will trigger all the executions that you need to do to return the values of the action. So one action, for example, is counting the elements. I have 8 elements on the list. So for counting, you need to read the elements. By the way, there are other ways for building RDDs. This is just the simplest. You can build an RDD from a text file, from a JSON file, from a database, and many ways. From an Excel file. So here, after you create the RDD, you can execute an action and request, okay, how many elements I have? You can also execute ask for, give me the 3 elements. I would like to see them. And this is something that we will use a lot because eventually you have something that is millions of numbers. So you are not able to gather all of them. Eventually you get an RDD that it is more than 1 terabyte. So you cannot put that in memory. You cannot gather all the elements in a list because there is no memory. We have 90 gigabytes of memory. If the data is 1 terabyte, there is no way you can put that on memory. But you can take 3 elements, a few elements, and you gather an idea what is happening there, and you move the needle of the execution of the algorithm, and you prepare the elements with that. So take is something that we use a lot. And collect, if the RDD is not that big, you can execute collect and gather that back as a list. Again, something that happens only if the RDD is small enough that you can put in memory them back. So now, transformations are things that you can do with every element on the data. I just mentioned in here 2 basic transformations. One is a map. It takes one element of the data and applies a function to it. So this is a function. It's a Lambda function in Python. A Lambda function is a function that is so simple that doesn't even deserve a name. You just enter the element that you need that it takes and what is the result of the Lambda function, period. So what I'm doing here is taking and creating a new RDD that basically computes the square of the values from the first RDD, from the original RDD. Notice that when you execute this, nothing happens. Only the action, that is the second line, the take, will trigger the execution of the data, the manipulation of the data, will trigger the execution of the functions for all the elements here. And if this original data, the RDD, were sufficiently large, it could perfectly divide this function in 2 portions, for half of the data in one core, half of the data in another core, and at the end, it will gather all the data to build the structure. So that's the beauty of Spark. It scales, something that you cannot do with other solutions, with other packages. And here, I am doing a filter. A filter is something that, depending if you return true or false, it will just gather the elements that return true. So here I am applying a function, and again, another function, show it tiny, that doesn't deserve a name. It takes one element. For each element of the function, please only if x is bigger than 5. With this, return, give me 3 elements. Well, those are the 3 elements that are there, period. Those are RDDs, and we will use those for machine learning. They are central for machine learning, or for building the elements that we use in machine learning. Now, data frames. Up to some point, now Spark start building a new API on top of what is called a data frame. A data frame, it has more complexity on top of RDD. At the end, it's an RDD with more strings attached, with more elements, more conditions. Those conditions are that you can put that as columns on a table, and you can give them names to the columns and properties, and at least a type for each column. For working with data frames, you use what is called a sparsation. So no longer a sparse context sparsation. Here I'm creating a sparsation called Spark. And now I am demonstrating here how you can take a list of tuples, and with those lists of tuples, build a data frame. So here I have the 3 first elements of the periodic table with some numbers, and I create an RDD. This is an RDD. Up to this point, this is an RDD. Now, with that RDD, I can say, okay, now build a data frame from that RDD where the columns are named like this. So I can use the names of those columns to manipulate them later on. And you can use this function show, and you will see a nice str table built for the data frame. You will just see the symbol, the name, atomic weight, atomic number for those elements, for the rows there. And also you can ask for what is called an schema. So an RDD with a schema, and you can create a data frame. In this case, the schema is what is the name of the column and what is the data type associated to that column. We never declare here the data type, but it can infer the data type from the elements. So you notice here that the symbol is a string, the name is a string, the Z, the atomic number, is an integer, and the atomic weight is a double precision number. So it is able to infer the types for each column. And again, this is very, very similar to the kind of structure that you have on Pandas. Pandas work with data frames, and they work very similar, except for the fact that in Spark, the data frames are based on RDDs. They are so in such a way that you can ask for the property, just strip out all the schema, return me the RDD, and you can do that. And sometimes you need to go back and get just the RDD. So from the data frame, you can ask for the RDD and return the RDD, and get the RDD and put the data, and the data will be a list of rows. And eventually you can, a row is an element inside Spark, and you can strip also that part of from it and return back the tuples, but we will not be doing that. So now, once we know the basic 2 building blocks for Spark in globally, now let's go back into my MLlib. MLlib works with 2 basic building blocks for most part, are vectors and matrices. And vectors can be local or distributed. So a local vector is a set of elements here where we have, let's say, And there are two kinds. It could be a dense vector, where every single value in the vector needs a memory location, location in memory to store it, or a sparse vector. And often we will be working with sparse vectors. We have long dimensionalities, but highly sparse elements. So in that case, it's a waste of memory to try to store a bunch of zeros for something that has less than 10% of the array with some non-zero values. So for dense vectors, you can use a NumPy array, you can use a Python list, and for sparse vectors, you can build an MLlib sparse vector, or you can build a matrix using something called a CSC. So we will see that. That is important because we usually are not so familiar with the sparse vectors in most cases, but they are important, especially for performance and scalability reasons. So let's start with this. So here, I am taking a list and I'm building a dense vector. This is one. Another dense vector from directly from the list. So in this case, it's a list. In this case, it's a NumPy array. And well, now, and a sparse vector. And a sparse vector here. And the sparse vector here is built with this method sparse, where you declare the length of the vector, the indices of the non-zero values, and the list of values in the sequence given by the indices. So with that, storing an sparse vector became very efficient. You don't need to store anything that is zero. You just need to store the values that are non-zero and the locations of those values in the array. And for a matrix, and this is important for the exercises in a minute, you can create that with the CSC representation. For this, notice how this works. You have the values that you want to store. Here, you have the indices of the values. Yes, let's see. Yes, the second part is the indices, and the third part are the pointers to the where and from which point to which point you will consider the indices for each column in the matrix. So let's consider, for example, this one. This one we are creating here. Very simple example. Here, we have an array, one column, two values, and the values are in the position 0 and 3. 0 and 3. And you will be taking the pointers 0 and 1. So this NumPy array will tell you, okay, which are the pointers that I will be using for the first column? It will be the 0 and 1. If you have a bigger matrix, this array will say, okay, how many pointers I will be using for the first column, and after the pointers for the second column, and the pointers for the third column. And those will decide which pointer it will take, which indices you will be taking here for each column in the sequence. So that's how you build a matrix when a sparse matrix using the CSC. Several codes, some SciPy used that, and that was it took. Another element for machine learning, MLlib, is a label point. Notice, remember that in classification, you have input data and some labels, some known results. This is a cat, this is a dog, this is a cat, this is a dog. So for that, a natural way of storing that is using a label point. A label point has a label and a feature set, an array of values. Yes, this is from Python and C. 0 means the first element. Yes, thanks for the observation. Yes, in other languages, probably in R, they start from 1, but in Python follows the C convention and it starts from 0. So 0 means the first element. Yeah, think right. What else? So here, notice that I have here a dense vector. We have a dense vector here, dv1. And with that vector, we will use that vector to associate that as features for one label point. And that's what we're building here. This is a label point. The value here is a double 1. And this is a set of features. It could be, for example, temperature, pressure, element this, element that, or it could be a signal. It could be the size of the weight of the animal, the height of the animal, the color. But it is something that if you can encode that somehow with numbers, that is something that you can put as features, and you can make a big array of that. Typical case for computer scientists that deal with something else. A typical example there is for houses. You can put the size of the land, the number of rooms, the location, the geographic location, and you encode that. And with that, eventually you can predict the price of that house. For scientists, it will be a set of physical properties that we would like to observe and we think are relevant for the problem at hand. Now, also, you can create a label point with a sparse vector, and exactly what I'm doing here. And a sparse vector here, 4 elements, 2 non-zero values, 1.6 on the first location, so 0, the first location, and 3.1 on the fourth location. It means index number 3. This is. And also there is another, well, I will not enter too much detail here, but also from data, from a text file, you can build a label point. So here I'm just demonstrating how that looks like. When you build the RDD here, you can see that they have a label point here and a long set of properties here, a bunch of numbers that we think are relevant for predicting, for associating the label 0. Now, matrices, those are for vectors. Those are for vectors. Now, matrices. Matrices, again, we have local matrices. We can build those as a dense matrix. So all the elements needs a location in memory to be stored. So with a dense matrix, you can have something like, say, 10,000 times 10,000 on our modern computers is okay. But now what happens if you have something that is 1 million times 1 million? You can no longer put that in memory, but I'm not so sure. 1 million times 1 million. I don't think so. It will be 10 to 12. Yeah, it will not. We don't have enough memory to store that. Even worse if each number is a double precision number. Definitely we cannot store 1 million times 1 million. But we can store it if it's sparse. If just 10% of the values or 1% of the values are non-zero, we can declare which values are non-zero. So this is a dense matrix, and this is important. And here is a sparse matrix. Same thing we are using the CSC convention for the matrices. So the number of elements, the rows, columns, the indices, the pointers, column pointers, row indices, and the values that we will store. In this case, let me see why we have this. Yeah, and we can try to convert this and see how this, you can see this on a dense matrix. And this is part of the first exercise that we will be doing. So let's stop a little bit to understand this, because this is crucial. Even you were still not into even the first part of the machine learning algorithm, but this is important. So 3 rows, 2 columns, those elements here. So we will be using from this one to this one. So the first element here, this index, to store the first value, 9, on the first column. So the first column is using just this index. We see that here. Now, the next column will use 2 indices, those 2, 1 and 3. And this one, 6, will be located for the in here for the last element, and 8 will go in the second element, 2 and 1. You will have the opportunity to explore that and recheck that in a minute, and we can go back. But let's move. Distributed matrix. Let me see. Now, I will not go too much detail. I just put it there because I would like to reach at least to a certain point. Now, imagine that you have something that is, let's say, hundreds of gigabytes of data. Each row, you can store it on one machine. You cannot store the whole thing in one machine, but you can distribute it. So you can have, for example, half of the elements in one machine, half of the elements in another machine, and Spark will be able to gather data from the different machines as needed for the algorithms to work. One way is using a row matrix. With a row matrix, you parallelize the rows across multiple partitions, multiple machines eventually. And you can gather the data that way. So I will not enter into the details. I would like to explore better the statistics. So now, I mentioned to you that central to this is at some point you cannot visualize things. If you are working in 100 dimensions, you can use PCAs and reduce a little bit that, but it's still, in many cases, you cannot visualize things. Just at the very end, when you have proceeded correctly, you can get some plotting, and you can use Matplotlib, Seaborn. There are several tools that are very good for plotting, for machine learning plotting. But still, the dimensionality is something that is on top of your shoulders, and it's something that blind you somehow. The only thing that gives you some light on the data is statistics. And that's why it's important. And even if before we enter into the machine learning algorithms, we need at least to know what we can do with some basic statistics. I mean, the MLlib offers some of that right away. So most of those things are here in this MLlib stat, the object statistics. For example, we are creating an RDD here. I create 3 RDDs, one with an NumPy array, another NumPy array, another from an iterable. Think about it as a list. In Python 3 is not actually a list, but anyway. Oh, here, no, it's a NumPy array built from an iterable. Okay, all of them are NumPy array. And now we can get some basic stats from those values. Notice that the values, the RDD is built with 3 rows. The statistics that we are getting are by columns. We are getting the statistics between the first column here, the zeros, the ones, the 2, 4, 8. We build the RDD with rows. We gather statistics from columns. What's the reason for doing that? It's because the whole point here in Spark is that eventually this is distributed. If we have all the data in one computer, well, it's okay. The statistics are relatively simple. But if you have one row in one computer, another row in another computer, to compute the mean, you need to ask for one element there, one element here, and make the average. So that is what this is doing, even if it's working in just the same on the same machine. So you are getting here the stats here, the mean. So it's computing the mean value here by columns, the variance, and how many non-zero values we have. So notice that here only the first row have just zeros, and other columns have a number of non-zero values. Now, this is one thing: basic statistics, means, variance. So now, correlations. Another important concept in statistics is correlation. This is the equation for computing the correlation. So it is based on the means. So you measure the distance between mean values. Just to save some time and give you a visual idea of what a correlation means, if you have the points, for example, a line on a straight line with a negative slope, they are negative correlated. The correlation is -1 if they are aligned perfectly on a line. If they are not so well aligned, but still they follow a trend with a slope that is negative, the value is negative, but it will be between 0 and -1. If the slope is positive, it will be positive. If it's just on top of the line, it will be exactly 1. And if there is no correlations, if the points just fill the space, not trend, you cannot see a trend. You cannot align, you put a line there where they follow the correlation is 0. 0 correlation. That's one. And MLlib give you a tool for computing correlation from series of data. And that's exactly, it's still in the statistics, MLlib, statistics. We are creating a couple of values here. What I'm doing here is creating one array with some randomness here. So up and down, so I am moving the dots up and down a little bit. 50 values. And now I'm here creating another one. 2 times that value with some randomness. So you see the values are spread, they are not perfectly aligned, but you can see immediately, okay, this should get us a correlation that is positive, is less than 1, but it's still positive. So the correlation, you can compute the correlation here with the statistics.core. And there are several methods. The method that I just put the equation here is the Parsons correlation, is this one, which is based on the standard deviations and means. So here you have the mean values and the standard deviations to compute that. And yes, so let me see. Oh yes, I put it here and I compute that. So we got a value that is really close to 1. Well, relatively close to 1, but still it's positive. It follows the ideas for a correlation. So something that we can compute with MLlib for that. Again, notice that these 2 series could be hundreds of gigabytes. So, and could be distributed across multiple machines. So they will do all the movements of data. Spark is smart enough to do the movements of data needed to compute the means that you need to know to compute for that, or to compute the standard deviations for the data, for gathering the data from eventually multiple machines. So that's it. And now, if you have just one series of data, you can compute the correlations between all the elements there. So now I have here 3 rows. My RDD has 3 rows, and I would like to see the correlations between all those 3 rows. This is a different concept compared to this one. Here we have 2 series of data. Here I am asking for, please correlate all of them by pairs and give me the values. So that gives us a matrix of correlation like this. You will see here, let's see, no, this, that the diagonal is 1. Of course, is you are comparing, you are making the correlation of the same array with the same array, so you get something close to 1. And all those numbers were very silly created, so they align very well. So you get perfect lines for them. So they are really, really close to 1. This is one thing that you can do, correlations. I didn't understand the p-values. This is the p-value. Oh, I did. I'm not sure that you can pose me the question later on, and I don't know. So this is the value that we are getting. So here, the row here, the row for the correlation is right here. I got it here. Correlation is this value here. So I got it from this value here. The query values, I think yes, but I need to check how. We will see later. We will see later. For those. Yeah, I think so. I think so. But I'm not so sure right now. I think yes, but not right off my head. And we can see in a minute the documentation for that during the exercise time. Now, what else? Okay, the correlations here, we got the value. Now, stratify sampling. Yes, we will see in a minute for doing the exercise. I think I'm relatively close to the exercise. So now, this is let's do this example for here. This is very similar we did last time during the previous workshop. We built an RDD from taking a book. So this is reading the Summa Theologica. It's a big book, many words there, from the Gutenberg project. So I am building an RDD with all the words in that book. Here I am applying a transformation to gather just the words. So splitting all those values, so the lines cut by words and gather those. So at the end, I have all the words there. And now I am building a key part RDD, which is something that we discussed last time in the previous workshop, which is basically having a label here and a value here. That is how RDD will be interpreted, a key value, the first element, second element. The key for us will be the length of the string. And now we will ask, okay, can we get a sample of this RDD that respects some statistics for the elements on the labels, for the keys? So remember, this is the key, 7. all the words with 7 characters will have that label. We would like that elements with 0 characters have 0 chances of appearing. Elements with 1 word, so in my RDD words with just 1 character, I would like to give them a very relatively small probability for appearing. And I would like to give better chances for words with 4, 5, 6 characters, and again give little to none probability, very low probability for big words. So I would like to sampling that set, just respecting the square. This is an algorithm, though this is something that you can do very efficiently by traversing in parallel the whole set. You divide the set, multiple processors will take each word. I will say, okay, how many layers? Which is the key? Okay, 7. Which is the probability for 7? It will throw a dice, see if the value is less than 0.2, it will take the value. Otherwise, it will discard. That's how that works. It's a very easy and parallelizable procedure. It will not be exact. It will probably not give you the exact number of values that you expect, but it will work. So that is exactly what I'm doing here. I am sampling by key here with those fractions. So for this, and I'm getting basically what I was expecting. Most of the values will be worse with 4, 5, 6. It doesn't prevent me from getting long words like this one, but it's just the chances that I announce. So this is another thing that we can use. For example, we know that we have a sample, male, female, and we would like to respect 50% probabilities of getting each one of them. We have labeled those in advance, so we can use this to gather something that will not have a special bias or some being just males or just females on my sampling. That's another thing. So it's again something that we will use in another exercise, in another algorithm. Hypothesis testing. So now there is a measure that we can use in the statistics to see if something is representative of a given distribution. Some observations can be, the population can be correctly fit a certain classes in the representation. So here we will see the equations for that, so we will try to skip that for a minute and show you that you can take a vector here. This is a dense vector that I'm building in Spark. And I am asking here how good that vector fits a uniform distribution of values here. It will give you a set of values that represent how good this vector is an uniform distribution. So here you get this a set of numbers that give you an idea of those of that statistic, how good that fits the others. I think that we'll use it here for another thing. Well, no, let's skip this here. I'm moving for the random data generator because the time is running short. So there is another thing here. For building random data. It's part of the MLE, where you can create synthetic data for exercises, for problems. And here we will be building a normal distribution centered on 0 with sigma 1. Yes. So it will give you the mean, of course, really close to 1, the standard deviation 1. This is exactly what we were expecting, the maximum and minimum value here. And from this, yes, and I'm here and applying a function to that anyway. So this is not the only distribution that we can create. In the documentation that is part of the exercises in a minute, you will see that they have Poisson, the normal, log norm. They have a variety of distributions that you can use for building series of data. Okay, now there is this other thing that is often used in machine learning. Is the kernel density estimation. Imagine that, and this is something that happens a lot of time. You got some values from experiments, you throw some coins or throwing dice, and after you are building some distributions, so a histogram. How you can try to make sense of that histogram? You have a very large number of values, and you use very tiny bins on the distribution, you will be getting holes in the histogram. If you use large bins, you will be very fat rectangles, but not much idea of how the distribution works. A kernel density estimation is something that builds with some distributions and a smooth curve that give you a visual idea of how an empirical distribution behaves or should appear, compared with the with just an histogram. So for making that example, or for showing that, what I'm building here, well, I'm generating some data with this function. Here I have a log normal, a normal distribution with different centers. So it will give me different bumps in two places. And I will try to build a kernel density for those cases. So here you will see, okay, those are the points that I'm getting. So the first set of points are those from the log normal, centered on 0. So you see here. And the second part here are those 3. So this one. So notice that those in the second part of the right side are centered on 3. This is exactly what I was asking here. Centered on 3. And they look like this when you put an histogram. With the kernel density estimator, I can build multiple soft curves, and soft depends on the size of the bandwidth that I will be using. More soft, less soft, depending on how big this value is. Here I am building 6 values just to show you how this differs when you use different values of it. And we will see in definitely in another workshop, how we can optimize the bandwidth for a very particular loss function. So we use a loss function to see which is the best fit for this. So at this point, we will not go into the optimization problem, just using different Bs, different bandwidths, you will be getting something with a lot of spiky elements because the bin is too small, or something that looks more like a soft curve here, that is closer to the ideal situation for this empirical distribution. And here I have a couple of exercises, and I'm not really sure if I will give you the time. I will just offer you the exercises here, and I will start a little bit in the next 50 minutes, a little introduction to the next notebook for machine learning. So let's describe, and we'll have 10 minutes, and in the next workshop on machine learning, we will be start digging into classification regression. So first one is to create a sparse matrix for a diagonal, to create a diagonal matrix and as a sparse matrix using CSC matrix. It's almost trivial, but try to do it. Also anti-diagonal matrix. So very, just to force thinking about the indices and the pointers for building a sparse matrix. Correlations. Okay, build two series that you want with an exact correlation of -1. Exact. So that is also trivial, but test it. Compute the correlation for that. Compute two series completely uncorrelated. Again, trivial. Random numbers, uniformly distributed, and test that how close that is to 0. And now this one, create a random sampling from the Poisson distribution. I think I can, if you will see here, what I told you. There is a relatively complete set of distribution here that you can use. I am asking for this one, for the Poisson, for RDDs. So build a Poisson distribution. And now try use the KDE with different bandwidths and play with the bandwidths for fitting that distribution with tiny little Gaussians for the that will mount. So basically doing exactly what is shown here. So tiny little Gaussians on top of that to recreate with a soft core the distribution, something that is not actually. So that's it. So now let's see the next notebook, at least the first part of that. So and for the next workshop, we will go directly into this workshop completely, into this notebook entirely. So same thing. Yeah, well, if I can execute this here. So now we will be introducing some of the first algorithms in machine learning. They're very classical. They are for supervised learning algorithms. Yes, around, yeah. First I think, yeah, first Friday of each month, effectively what we have on April. So supervised learning algorithm, classification or regression. I will probably not dig much. I will just show you the idea, not what the math behind, because I would like to discuss math compared with the I did like before for the kernels that I was rushing on that part. One part is support vector machines. The idea here is something like this. You have elements on two sets, and we would like to capture, again, this is simple. This is very easy to visualize because it's just 2 dimensions. And it's from a very classical problem in machine learning, the iris data set. So we have a set of properties here that identifies this plant as being from one specific variety compared with another variety. And you can see, of course, if I give you another point here, can you identify which variety it will be? So you can see, okay, yes, if it's larger than 3, it probably belongs to the blue side. If it's less than 2 here for the x-axis belongs to the. How we can trace a line, we can build a line here that divides these two sets nicely. You can make many lines here for this. So you can throw a vertical line, and that's one way. You can make an horizontal line, that's another way, and separate those two sets. Which one could be the best choice? Both ways, we are separating the sets entirely. So one line here, vertical, one line here, horizontal, around 1.6 or around here. We are building a new line. There is a better way of dividing that, and the support vector machines answer that question. It's basically trying to gather one point here that is, let's say, the last point in the frontier of the yellow zone looking into the blue zone, and the first point in the blue zone facing the yellow zone here. I'm making a point right in the middle and tracing a line that is perpendicular to the vectors that we put. Those are called the support vectors, and we are drawing a line that is perpendicular to those. That's one of the problems. We will see the math here. So yeah, exactly what I have here in the video. So we have several ways of partitioning this for the classification but there is one way that is more elegant, natural, and beautiful, and is exactly using those pink points. They are called the support vectors, and use them to draw a line that cuts the regions in such a way that they are naturally dividing the area of the space. You can generalize that for multiple dimensions, no longer visible, but this is exactly. And that moment, what you are doing is a hyperplane that will divide those regions. And logistic regression is another thing that we will discuss in the next workshop. The word regression is misleading. Because it's used for classification, and even worse, it's using for binary classification. It's using a logistic function, a function that is squish values on the top, on the bottom, to classify something. If the value that we get is bigger than 0.5, it will go directly into the top. The value that goes beyond that, it goes to the bottom. So it will do binary classification using this curve that separates that. And I think I was doing something like this. I was trying to use the same exercise, 2 dimensions, how to make a line or something that separates that, saying which value should I get for a point here in the middle. Imagine a point in the middle of the plot, of this plot. Give me a value. A support vector machine just will give you if it belongs to the blue or the yellow. The logistic regression will give you a value, and that value weights how much it belongs to the blue versus to the yellow region. And that's it. So I think the time is short now, and I was trying to gather an idea how far I can go with this. For the next workshop, it will be classification, regression, and clustering. I think that it can go that, and eventually the recommender, which is an alternate method, linear sparse. We'll see. In April, May, we will have another workshop in more advanced methods. So eventually we will go in more Bayesian methods, random trees, so a little bit more sophisticated. All those materials are on Thorny Flat, in the location that I just give you in here. So if you go here, that will be and you can copy the materials. So the notebooks uses the figures and data that is alongside. So if you go here, so what? I would go to the location, Shield Software, mini workshops, Spark, Python. So the materials are there, and I will be updating the materials for the next workshop. The notebooks are in the notebooks. The MLlib are the examples directly from the sources of Spark. The inputs are data that I put there. So just to differentiate where the data comes from. And images are the images, the nice GIFs that I put for visualizing the PCA, for visualizing the clustering. So the figures are there, so the notebooks are self-contained and doesn't require internet access for getting the images. And you can take those materials from there. So you see in the notebooks here, and I think they are updated. I need to check, compare with my copy here locally. The introduction to Spark, that was the topic from the previous workshop. And eventually I need to grow the Pandas API. So the relation, I just move, I make a leapfrog and move into the machine learning and skip the data analysis part, which is the relation between Spark and Pandas and how you can move data frames from Pandas to Spark and back and forth. I'm not super sure. Daniel, do we have?
Give me 1 second, I'll link it.
Okay. From the previous workshop where we discussed very softly the RDDs. Yes, so Daniel could just post the location for our previous workshop. It was RDDs, actions, transformations in more detail. So how you make maps, map by keys, key pairs. I just described those really quickly because I know some people who attend this workshop didn't attend the previous one. So when I start building the RDDs for making the vectors, for making the matrices, you will be getting those. So that's it. So thank you very much for your attention. Thank you very much for most of you stay until the very end. Again, this is a series of workshops that we just started 1 month ago, and it will be all machine learning and all then related to Spark. So classical, what I call classical machine learning. So classical machine learning is machine learning except deep learning, except neural networks that has hyperinflated today in the machine learning scope. So this kind of traditional methods or classification, regression, clustering, random forest, Bayesian methods, so all those things, base method, right? All those things that Spark provides a solution for them in a distributed fashion. And the singularity image is something that if you want, you can take the image with you. There, let me see, can show you the image. So if you are running Linux and you don't want to install Spark and you want something that ready to use, you can go here, share containers, Jupyter. And here I have the PySpark notebook. So you can take this file. I think it's not that big actually. Well, it's 900 megabytes. It's still something that you can transfer to your own computer. If you use Globus, you can transfer that. And if you are running Linux or a Mac, I think, or you can use it from a Mac, you can use Singularity, which is a container engine, to run these notebooks from a container, from a Singularity container. Or if you are using this on another machine that has Singularity on it, you can run the Singularity. It is the very latest version of I rebuilt the Singularity image today. So it has the latest version of Spark and a quite recent version of all the underlying Python packages. So Matplotlib, Python itself, IPython engine, all that. So it's a very recent build of that notebook, and you can use it for reproducing all the materials from today. So yeah, feel free to take all the materials and reproduce all what we did today. You can do it in your computer, because we are not using anything that is even a megabyte of size. They are very small. The whole point of introducing you to this is that when you move into real scientific problems, typically dimensions grow much larger, and the size of the data grows much larger. So it could be gigabytes more of data. And I have used some of those things for a few gigabytes of data. So probably you can still put it on one machine, but you take the advantage of processing with 40 cores instead of what you can do with scikit-learn, that you will be limited for relatively small problems. So thank you very much. And next week, or next month, for the next workshop, we will be entering now directly into the methods that we discussed. Thank you very much.